Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Last session we did some probability or a probability worksheet. Today we are going to do a statistics one. Um, well, that would leave us with only trig functions. So I will have to briefly introduce what these are. Then we are going to probably have another session of trig identities. Or maybe I will combine. No, that would be too long. And then we'll have one on solving trig equations. And finally, graphing transformed functions of trig. Um, so we have like five. Okay. I think, yeah, I decided to combine a few, like post more than one video on a day. So probably I will go back and change the dates because I'm taping these earlier than so today, for example, is July 22nd, and I will not post this until probably sometime in August. But I will try to cram them so you have time to review the material and solve back exams before your Regents. Okay, so this one, I think the first few are, well, let's go over. A student decides to do a statistical analysis of the rainfall in a certain area of the country over the course of a specified 30-day period. What type of study does this situation most likely require? Well, since you don't have control on rainfall, you cannot say, oh yeah, you can check the weather, but don't rely on that. Let me be nice. Okay, so since you don't control anything, it's not a design experiment. You cannot design to have rain tomorrow at 4, for example. Okay. A random analysis, an observation. That's you are going, you see, the student decide to go and observe uh, the rainfall during 30-day period. A group of students want to, I think one is, well, okay, wants to know the most popular lunches in the cafeteria are during the month of February. They will have students fill out a questionnaire at the end of each period, every day, analyze the data through the month. Which one is that? That's a survey since they give them stuff to fill up. And as the sample size increases, the standard deviation of the sampling distribution always of the sample proportions or means or anything, always the standard deviation decreases when you increase the sample size. The reason is so easy. So suppose I walk into your classroom and I want to get an idea about, what was the average on the last exam. So I pick a student at random and ask her, so what did you score, sweetie, in the last exam? And she would say 92. I say, okay, so I'm going to use that as the average. What? That's that's dumb, right? Because I can come another day and pick another student, and that student has failed. And he said, well, I got 45. And you say, okay, that's the average of this class. They seem to be horrible. But if I pick randomly select like 5 or 10 students out of, say, a class of 30, and I average that, the error would be smaller. Common sense, right? So as the sample size increases, the sampling distribution, the standard deviation will decrease, which is B. Okay, number 4, the scores on a test approximate a normal distribution with a mean of 72 and a standard deviation of 9. About what percent of the students taking the test receive scores greater than 90? Okay, so we can use the calculator easy. We go to distribution and we get the cumulative, normal cumulative distribution. We enter the lower limit. We want above 90. So we can say 90. And then we want to enter infinity. We can't enter infinity. So the best way to do it is to say 1 EE, say 99. So 1/10 of a Google. Okay, comma. The mean is 72, comma. The standard deviation is 9. And I enter. I get 0.0227, which is roughly this is 2.275%. And they say approximately, so it's 2.5. You know what? 90 is two standard deviations above 72. Why? Because the standard deviation is 9, and 9 times 2 is 18, plus 72 is 90. And I know that 95% of the distribution is between negative and positive 2 standard deviation, right? That's what I mean. Here is the normal standard deviation. If this distance is 2 sigma, and this distance is 2 sigma, then this area is 0.95, roughly. I mean, it's 0.945 something, but roughly, I'm sorry, 9545. So if this is 95%, this number is 90%, by the way, 90% in the 90 as the score in the test. And this is 72, and this is 18. 72 plus 18 is 90. So I know 95 are here. So the other 5% are 2.5 on the left and 2.5 on the right. So above 90, there exists roughly 2.5%. Okay. But if you can use the calculator, it's easier. As the sample size increases, the mean of the sampling distribution is what? Does it remain constant? Yeah, absolutely. Changing that doesn't change the mean of the sampling distribution, meaning the mean of the means. So that remains constant. The standard deviation decreases, but the mean doesn't change. Which one of the following is a true statement about the differences between an experiment and an observational study? An experiment imposes treatments to observe the effect of some response, while an observational doesn't impose. Yeah, that's it. Non-humans are always the subject of observation. No. An observational study can produce a cause and effect. Now, we don't have cause and effect here. Observational study randomly assigns the treatment groups. No, in observation, you don't have any control. You just observe. So it's a. Okay. It's just I wanted to get this out of the way quickly. And now we have some problems. Nice. A college math course has one section of 240 students and 8 sections of 30 students. Wow. What college is that? Okay. Just try to visualize that you go into an auditorium to give a lecture and you have 240 students. I mean, it's almost impossible, but again, mathematicians love these things. What is the best explanation for the following misleading statement? The average class size is 53 students. Yeah, of course, these are like 480 divided by 9, you get the average. So what's misleading? Definitely this thing. This is outlier, right? If I didn't have that, the average is 30. So it jumped to 53 because of that. Okay. The average class size was rounded down instead of being round up. Okay, if you select that, there's no reason to continue the test, right? Just kidding. I'm so mean. Shouldn't say that. I know. Feel ashamed of myself. Most of the classes have fewer than 53 students, so the mean is not a good descriptor. Yep. I can use the median because the median is insensitive to outliers. When finding the average of the total number of students taking the math class was only divided by 8 instead of 9. A class of 240 is 8 times more likely to influence oh, yeah, I think this is the one. Most of the classes have fewer than 53, so the mean is not a good descriptor. Is it B or D? Because a class of 240, no, I think it's D. The class of 240 is 8 times. No, 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 no. It's B. I didn't read it. Is 8 times more likely to influence. What does that mean? It will influence anyway, not 8 more. 8 times more. Okay. No, I think it's B. Alrighty. In the accompanying diagram, about 68% of the scores fall within the shaded area, which is symmetric about the mean X bar. The distribution is normal and the scores in the shaded area range from 50 to 80. I know that roughly 58%, I'm sorry, 68% lie between plus or minus 1 sigma, right? So if we say this is negative sigma or x bar negative x bar minus sigma, and this is x bar plus sigma, then that distance uh is 2 sigma, right? Yeah, they want the standard deviation. So 30 equals 2 sigma, meaning 15 is sigma, so the answer is C. If you don't see that, okay, uh, I think it's easy. I don't know. We should know that 68, in fact, around 68.3% lie between plus or minus 6 sigma. So the number 68 here, 68% is important. Another way to say it is to standardize these or find the score. So the score here, when this number is 65, you get 0, right? And uh, this area is 0.34, and this is just sigma, one standard deviation. So that distance give you that. So maybe we can do the inverse, right? You have that, right? Inverse normal. I can't remember what you enter first. You should enter X and do we enter the probability first? No, I don't know how to do it with the calculator. I usually use Excel or some other software. But the easiest thing is if you remember that between plus or minus sigma, you get 68%, 2 sigma, you get 95, 3 sigma, you get roughly as a whole uh, distribution 0.997273. So it's roughly more than 99.7%. If the mean on a standardized test with a normal distribution is 54.3, the standard deviation is 4.6, what's the best approximation of the percent of the scores that fall between these two numbers? So between the mean and this number. Okay, so we can do again distribution cumulative. I enter the lower limit, which is 54.3, comma, the upper limit 63.5, comma, the mean is 54.3 again, and the standard deviation is 4.6. So you get roughly, yeah, 47.5. It's 47.7. 1,000 students took a test resulting in a normal distribution of the scores with a mean of 80 and a standard deviation of 5. Approximately how many students scored between 75 and 85? Notice that 5 is the standard deviation. If I subtract it from 80, I get 75. If I add it, I get 85. So identical to this problem. I know that 68.3 or 68% of the students will have a grade between 75 and 85, 68%. So if they are 1,000, 68% of 1,000 is 680. Or you can repeat that and say, okay, here is the normal cumulative. I have a lower limit of 75, an upper limit of 85, a mean of 80, a standard deviation of 5. So easy. And you get 0.68. You multiply that by 1,000 because there are 1,000 students, so you get 682, which is approximately 680. A normally distributed set of data, I mean, okay, has a mean of 59.6 and a standard deviation of 5.3. Find the z-score of 63. So we know the z-score equals x, which is 63, minus the mean, which is 59.6, divided by the standard deviation, which is 5.3. 63 minus 59.6 divided by 5.3. And you get 0.642. Notice cannot be negative. It's negative if you are below. If this number, uh, 63, instead of 63, if it were, for example, 53 or 50, yeah, you may get that. So you can exclude this. But anyway, here they shuffle the numbers, but a population is approximately normally distributed with a mean of 121 and a standard. They are all the same. No, I don't think we are wasting time here. So we'll do this and then look at the next page. So the minimum, the maximum, the mean, and the standard deviation. 0.262, let's see. Okay. Let's move here. Anne has a coin. She doesn't know if it's a fair coin. So she flipped it 100 times and get 73 heads, 27 tails. That's bad, right? It's a biased coin. It gives more heads, like almost 3 times heads than tails. By the way, I give in the probability and statistics playlist, I give a problem and I say, suppose you have a biased coin, but it's the only coin you have, and you have to use it between two players, but you want the result to be fair. How would you devise such an experiment? This is one of the problems I like because I've never asked the student and got the right answer. I think I give away the answer in that video. If you want to watch it, uh, be my guest. So she ran a computer simulation of 200 samples of 100 fair coin flips. The output proportion was like 0.497 heads and 0.503 tails. And the standard deviation was 0.05. So we know that this is biased. I mean, it's telling that to you. It's not fair. Given the results of her coin flips and of her computer simulations, which one of the following statements is most accurate? 50 of her next 100 coins flips will be head. Nobody knows that. Her coin is not fair. Yes. Her coin is fair. Yeah, absolutely. If I select head and I can play against you, yeah, it is fair. Yeah. It is fair that I always win. Yeah. Okay. 73 of the computer. No, this is ridiculous. Okay. Last question. Given an approximately normal distribution of scores with a mean score of 148 and a standard deviation of 21, use a graphing calculator without computing the z-scores to find indicated probabilities to the nearest thousandth. What is the probability that you get more than 140? Oh my God, we keep using the same function over and over again in this weird thing. So you want to score more than 140. So the less is 140, the maximum is EE99. So I usually use a mean of 148, standard deviation of 21. To the nearest 1,000 is 0.648. Randomly selected score is less than 176. Okay, so, well, why did I do that? So the least would be negative 1 times e to the 99, so negative infinity. And the upper is 176, but the mean and the standard deviation are the same. So here I get 0.909. Between 142, so okay, let's do it. There is no reason to. Lower limit is 142, upper limit is 172, mean is 148, standard deviation is 21, right? Did I enter the numbers correctly? 0.486. So 648 and 486 again, shuffling the numbers. I love these things. Okay, so again, I don't know. They didn't have anything about, the box and whisker plots or whatever, which you can use the calculator to plot it, or the first and third quadrants, quartiles, and you know, I didn't see any of that. But I went over probability and statistics or statistics for Algebra 1 in the Algebra 1 playlist. You may find one of them. You may find the video there if you want to skim and just watch it if it helps. I think that leaves us with trig, which we will start in the next session. If you have any comments or questions, please feel free to drop me a line. I will get back to you as soon as I can. Otherwise, thanks for watching, and I hope to see you soon. Have a great day.